Okay, good morning. The first speaker of today is Marcelo Atallah from Montreal. He will talk about fixed points of small Hamiltonian diffeomorphisms and the flux conjecture.
Well, thank you for the introduction, and thank you for the organizers for the invitation. This is very special for me. This is where I did my master's, so it certainly feels like homecoming. So I've been to this lecture room so many times to watch plenty of lectures. It's very nice to be on the other side today. So I hope I don't disappoint. So what I'll be talking about today, this is joint work in progress with Yegor Shalukin. And the story I want to tell you about is how some of the Arnold conjectures relate to the flux conjectures, and perhaps say a few new things about each. So let's first cover some basics, which have been covered here before, but since it's a Friday, I guess I'll start a bit slowly. For me and throughout the whole talk, M omega will be a closed symplectic manifold. And as most of you know, a Hamiltonian diffeomorphism is the time one map of a Hamiltonian of an isotopy induced by a Hamiltonian vector field, which is defined by this Hamiltonian relation. And I guess what I'll add that hasn't been said before is, in some cases today, we'll take this one form, which is usually exact in the Hamiltonian case, to be just a closed one form alpha, and that's going to induce, in the same way, a symplectic vector field and a symplectic isotopy. And just one little thing. We say that a Hamiltonian diffeomorphism is non-degenerate if its graph, which sits inside M cross M, intersects the diagonal transversely. Okay. So let us quickly recall what I mean by, there are no conjectures, at least for today. So first, the non-degenerate case, the Arnaud conjecture states that the number of fixed points of a Hamiltonian diffeomorphism is going to be bounded below by the Morse number of your symplectic manifold. So the minimal number of critical points that a Morse function can attain. And by the Morse inequalities, this is known to be bounded below by the total Betti number of your manifold. Now, there has been plenty of work on these conjectures, and in fact, this lower bound here is now known in full generality. I prepared a slide for the end with plenty of notable contributions, but I'll leave it for the end because otherwise I won't be able to finish the talk. But this case here, this is known in when the manifold is aspherical and in just a few other cases. So it's open and it's not known in full generality. And more generally, so without the assumption of non-degeneracy, the conjecture states that the number of fixed points of a Hamiltonian diffeomorphism must now be bounded below by what I am denoting here by crit M, which is the minimal number of critical points as any smooth function must attain on your manifold. And by the Stirner-Schnirelmann theory, this is bounded below by the cup length plus 1 associated to your manifold, where the cup length is just the maximal length of a chain of cup products of cohomology classes of positive degree. So in the case of a symplectic manifold, because, the symplectic manifold is closed, we know that taking the wedge product of omega n times with itself gives you a volume form, so it's non-trivial. So the cup length is at least n, where n is half the dimension of the symplectic manifold. And in this case, even knowing this lower bound, it's open in plenty of cases. It's just known for aspherical manifolds. And in fact, even Fleur believes that it might not be true in full generality. Let alone this inequality here. Okay, so now let's go into the flux conjectures. So we have here this sequence of inclusions of subgroups of the group of diffeomorphism of your symplectic manifold, so diffeomorphisms from M to itself. Simp here, these are just the symplectic diffeomorphisms, so right, the ones that pull back the symplectic form to itself. Simp 0, it's the path component of the identity. And Ham, well, the group of Hamiltonian diffeomorphisms. And this was already defined, I think, in Yegor's talk, but for a fixed choice of Riemannian metric on your symplectic manifold, this induces a distance. And in particular, one can define the C0 distance on the group of diffeomorphisms just by taking the supremum of the distances between the images of the maps. And we can then think of the C0 topology as the topology induced by this distance. And we're going to be looking at the subspace of the C0 topologies. And similarly, you can think about the C1 topology, which also cares about the first derivatives of these diffeomorphisms. And OK, now interesting question is to ask if in each of these inclusions, is the subsequent group closed inside the following? And well, for this first inclusion here, well, in the C1 case, simp is clearly closed in diff because the condition of being symplectic is a condition on the first derivative, so it's pretty easy to show that it's closed. And it's also, in fact, closed in the C0 case, and that's the content of the theorem of the famous theorem of Gromov and Eliashberg, but that's a lot harder to show. So simp is C0 closed in diff. So if you have a sequence of symplectic diffeomorphisms converging to some to some diffeomorphism in the C0 sense, that implies that the limit point is also symplectic. Now, the second inclusion here, again, the C1 case is not that hard. It's known. So simp 0 is C1 closed in simp. And this is basically, this follows from the fact that simp is locally path connected in the C1 topology. So basically what happens is when you have a C1 small symplectic diffeomorphism, you can look at its graph in a Weinstein neighborhood of the diagonal, and that's going to be identified with the graph of a closed one form, and then you can look at the deformation that takes that to the zero section. And that's going to correspond to a symplectic path that connects you, a small symplectic path that connects you to the identity. But in the C0 case, pretty much, this is pretty much open. I guess maybe just for spheres, it's known, but apart from that, at least to my knowledge, nothing is known. Now, the flux conjectures, they deal with this third inclusion here. And again, in the C1 case, you want to ask, is Ham C1 closed in Sim0? And in this case, it's not a conjecture, it's a theorem, and it was proved in full generality by Ono in 2006 with a lot of previous progress by Lalonde, McDuff, and Polterovich in 97. Now, the C0 case, there has been some progress, but much less is known. And well, in 83, Armand proved it for symplectic tori. And after that, there has been, in the same paper as in the C1 case, Lalonde, McDuff, and Polterovich had a little bit of progress there. And then the state-of-the-art result is by Buchowski. And before I go into what they did, I have to go into some definitions. But this is the key point here is that this identification that we have in the C1 case of the graph of the symplectic diffeomorphism with the graph of a closed one form, this is not true in the C0 case. Right? You're going to be small, you're going to be inside a Weinstein neighborhood, but you can approach the diagonal in a pretty non-graphical way. So that usually the problem becomes much harder because of this distinction. So now I'm going to define the flux map. Usually we just define the flux homomorphism, but I'm going to take a slightly more general approach so that I can finally define the topological flux group. So let map 0 denote the space of smooth maps from M to itself, which are homotopic to the identity. Now, the flux map is going to be a map that takes a class in the universal cover of map 0 to the first de Rham cohomology of your manifold. And the way this map works is, well, classes here are represented by paths of smooth maps, which are based at identity. And we want to be able to evaluate one cycles, right, because we're going to be in H upper 1. So if gamma is a one cycle, what we do is just we use the map to flow this one cycle. We get some sort of cylinder, and we compute its symplectic area. One can show that this is well defined, and furthermore, it respects composition in the sense that it sends composition in the universal cover to a sum in H upper 1. And in fact, when you restrict the flux homomorphism to the universal cover of Simp 0, then it's a homomorphism, because that's a group. The topological flux group is defined as the image of the fundamental group of map 0, seen as a subspace of the universal cover by the flux map. And because of this property that it respects the product, well, this is going to be a subgroup of H upper 1. So this is what I'll call the topological flux group. So these are fluxes that comes from loops of smooth paths. Not necessarily diffeomorphism, not necessarily symplectic, just smooth paths. Okay, so there's quite a bit of information here, but let's go slowly. In the case that when we restrict the flux homomorphism the flux map to Simp 0, that's a homomorphism, like I said, and by a fantastic result of Banyaga, the flux of a symplectic path, it's 0 if and only if that path is homotopic with relative endpoints to a Hamiltonian path. So in particular, if you have a symplectic path with 0 flux, that means that the endpoint is a Hamiltonian diffeomorphism. So now let's look at this commutative diagram here. So in the bottom, we have this sequence of inclusion, and the only thing that I haven't defined yet, and I will now, is what I'm denoting by Ham 0, which is simply the C0 closure of Ham inside Sim 0. So of course, Ham includes into that, and that Ham 0 includes into Sim 0, and Sim 0 by definition includes in map 0. And let pi here be the canonical projection of the universal cover of Sim 0 to Sim. So, okay. Now, we can look at the pre-image of Ham 0 by pi, and what are these? Well, these are classes in the universal cover of Sim 0 that can be represented by symplectic paths, which are based at identity and whose endpoint lie in Ham 0, right? The C0 closure of Ham in Sim 0. Okay, so now let's define the flux group. This is the usual, what people say, mean by when they say the flux group. Well, that's just a image of the fundamental group of Sim 0 seen as a subspace of its universal cover. So these are just like, these are fluxes of loops of symplectic diffeomorphisms. But this can be defined in an equivalent way as the image of the pre-image by pi 1 of Ham. So again, these are classes that can be represented by paths of symplectic diffeomorphisms, but now this is Ham and not Ham 0, whose endpoint is in Ham. But why do we have this equivalence? Well, if you have a path whose endpoint is Hamiltonian, right, this starts at identity, this is some Hamiltonian diffeomorphism, then you can either concatenate or compose with an exact path, a Hamiltonian path, and that has no flux by the observation I made in the beginning. So that's going to just be a symplectic loop, and all the flux is coming from the symplectic part of the path. So that's how you get this equivalence. And the reason why I want to define the flux group in this way as well is because it's much easier to generalize to the C0 case, to obtain the C0 flux group. And just before I talk about that, just let me point out that by the result of Banyaga, you have this short exact sequence where this map is just the descent of the flux homomorphism to Sim0. So this basically means that the difference of Sim0 and Ham is completely captured by the quotient of H1 by the flux group. In particular, if you're a simply connected symplectic manifold, these groups are going to be equal. Now, the C0 flux group, like I just said, is defined analogously to the flux group once you have this definition in mind. But now we take the pre-image of Ham0 by the projection. So, well, I keep saying, well, the flux group, these are fluxes of loops of symplectic diffeomorphisms, and we would like some sort of nice characterization of gamma 0. Because a priori, what are these, right? These are just fluxes of paths whose endpoint lie in Ham0. But okay, these are not loops, but they can be represented by what we informally call almost loops. So what I mean here is that elements in the C0 flux group can be seen as the flux of a symplectic of a path of the symplectic diffeomorphisms whose endpoint is arbitrarily C0 close to the identity. So you can, okay, you're not a loop, but you can take this endpoint as close as you want. And the idea is basically, you know that for any class you pick, the endpoint is Ham0. So you can just take a sequence of Hamiltonian diffeomorphisms that approach that endpoint and use that to bring it close to the identity, C0 close to the identity. So why did I spend some time talking about the flux groups? Well, because usually the flux conjectures have a nice characterization in terms of the flux groups. So in the C1 case, the C1 flux conjecture, which, well, asks if Ham is C1 closed in Sim0, is equivalent to showing that the flux group, the usual flux group, is discrete as a subgroup of H1. And this is precisely what Ono showed in 2006. Now in the C0 case, the C0 flux conjecture, this is equivalent to showing that the C0 flux group is equal to the usual flux group. And in particular, that implies that the C0 flux group is discrete. Now, the way back here, it's not known. We don't know if it's true. And the reason why it's hard to show comes back to what I pointed out in the beginning. This equivalence comes from the fact that the graph of a C1 small symplectic diffeomorphism is identified with the graph of a closed one form. And this cannot be done in the C0 case. And that's where this the distinction lies. But if you know that gamma 0 is discrete, that would already be pretty good indication that the C0 flux conjecture is, in fact, true. Okay. This is what I just remarked. So now I can talk what is the state of the art in the C0 flux conjecture. So Puchowski in 2013, well, he showed that if the topological flux group is equal to the symplectic flux group, let's say, then the Ham is equal to Ham0. Then the C0 flux conjecture is true. And this is what Lalonde, McDuff, and Polterovich showed before in the Lefschetz case, so in particular for Kähler symplectic manifolds. However, showing that the topological flux group is equal to the flux group is almost impossible in most situations. So it's very hard to extract classes for which the C0 flux conjecture is true from this statement. Basically, you can say that if your symplectic manifold is aspherical and Euler characteristic is different than 0, or its fundamental group has finite center, then flux conjecture is true. But apart from that, it's pretty hard to be able to calculate this. Okay, so now I think it's a point to connect the two conjectures. And we do this in the proof of what I call here theorem A, is, well, we showed that in fact gamma 0 is a discrete subgroup of H1 for all closed symplectic manifolds. So in particular, this provides a new proof of the C1 flux conjecture. And like I said, this does not imply the C0 flux conjecture, but it does give a strong indication. It's like you can think of it as a weak C0 flux conjecture, because it gives you quite good indication that it is true in general. We do prove the C0 flux conjecture in some new cases, which I'll go over in the end. But the result I want to focus on today is the discreteness of gamma 0. And while the discreteness follows from two statements, the first is the main subject of today, which I call proposition 1, and it says the following. If you can assure that every C0 small Hamiltonian diffeomorphism has at least 2 fixed points, then gamma 0 is discrete. And what we do is, well, we show that if gamma 0 has an accumulation point, then we can construct a C0 small Hamiltonian diffeomorphism with at most 1 fixed point. That would in particular be a counterexample to the Arnaud conjecture if that were the case. And the second statement here is that, well, if phi is a C0 small Hamiltonian diffeomorphism, then the number of fixed points is bounded below by the cup length plus 1. And like I said before, this is greater than or equal to n plus 1. So in particular, this is greater or equal to 2, which is what we need for proposition 1. So putting proposition 1 and proposition 2 together, well, that yields the discreteness of gamma 0. Here, just a quick remark. If we assume furthermore that phi is non-degenerate, we can get stable Morse number here instead of cup length plus 1, but all we need is 2 for proposition 1. Yes? Sorry, C0 small. Yeah. Well, for small spectral norm, that's actually part of another work in progress, and it's probably true as well. And then it would be a matter of also showing that the spectral norm is C0 continuous, and then you would get this result automatically. Like if you know that you get the cup length estimate for Hamiltonian diffeomorphisms with small spectral norm, and you know that the spectral norm is C0 continuous, then this statement would just follow. Just in a few cases. So we know for negatively monotone, Calabiao that Yegor was talking about, and aspherical. But for that's for this is for that's why it's hard. Yeah. And theorem B actually follows from a more general theorem, theorem C here, which states the following. Well, if phi is a C0 small Hamiltonian diffeomorphism, and well, in particular, its graph is going to be in a Weinstein neighborhood of the diagonal. And so you can ask, well, this is a Lagrangian in some codisk bundle. Well, you can ask, well, is this Lagrangian an exact Lagrangian? And the theorem states precisely that if phi is sufficiently C0 small, the Lagrangian is exact. And then theorem B then becomes a question about intersections of exact Lagrangians with the 0 section. And this is what I remark here. Well, how do you get from theorem C to theorem B? Well, the number of fixed points of phi, this is just going to be equal to the intersections of the graph of phi with the diagonal. And by the identification of the Weinstein neighborhood of the diagonal with the codisk bundle, that's just the number of intersection points of an exact Lagrangian and the 0 section. And then you can just use some Listerner-Sneerleman type argument for spectral invariance of exact Lagrangians, and you obtain the cup length estimate for the C0 small Hamiltonian diffeomorphisms. Okay. Just a quick remark here. When M is rational, meaning that the symplectic areas of spheres form a rational subgroup of R, then theorem C, the exactness of the graph for a small Hamiltonian diffeomorphism, it follows from easier arguments which are already implicit in the work of Lalonde, McDuff, and Polterovich, and the work of Buchowski. However, in those cases, well, rational approximation doesn't work because the epsilon that you obtain for each rationality constant, well, it tends to 0 as the rationality constant tends to 0, which is exactly what happens in the irrational case. So you cannot just simply argue by rationality. Okay, so let's go back to proposition 1, right? So let me just recall what proposition 1 is, and because this is going to be where I'm going to spend the rest of the rest of the talk on. We want to show that if gamma 0 has an accumulation point, then we can construct a Hamiltonian diffeomorphism with at most one fixed point. So how do we do that? The main, well, external ingredient to the proof of this proposition is this great theorem by Farber and Schutz from 2006 that shows that for any closed manifold, every non-trivial first cohomology, well, a cohomology class of degree 1 can be represented by a closed one form which has at most 1, 0. Now, what we want to do is be able to extract some more quantitative information about this representative. In particular, we want to be able to control its C1 norm. And but why do we want to do that? Well, once we have a representative with few zeros and we can control its C1 norm, the symplectic path that this one form is going to induce, right? Well, it induced by, you define a vector field just by this defining property. If the C1 norm is small enough, then the time one map of the symplectic isotopy you induce will, the fixed points of that time one map will correspond to the zeros of your one form. If you don't have control over your C1 norm, perhaps you can get periodic orbits that don't come from zeros. So the first part of the proof of proposition 1 is showing this lemma. And what this lemma says is for a choice of norm in this vector space, right, H upper 1 is just some real vector space, you can you have a map sending non-trivial classes to representatives such that the representative has at most 1, 0, and such that the C1 norm of the representative is controlled by the norm of the class. And this C is uniform. So how do we do that? Well, okay, let's try to see. So first we take some non-trivial class, and you can assume that it has norm 1, just to make it easier, and take the representative given by the Farber-Schutz theorem. So that's a representative. It's going to have at most 1, 0. So its graph is going to look something like what I have here in blue, just 1, 1, 0. So this is the cotangent bundle, and we're looking at its graph. So we can pick some small neighborhood in N of this 0, and we can find some delta for some choice of metric in this cotangent bundle that captures the distance from having a 0, right? How far you are from having a 0 away from this U in simple terms. Now, for a sufficiently small epsilon, you can represent classes in an epsilon neighborhood of the origin in terms of the fixed norm that we have, right, in H upper 1. You can represent these small classes by closed one forms whose C1 norm is less than delta over 2. So basically I'm saying that if you go very close to the origin, you can represent each class by a representative whose graph is going to look something like this with a small C1 norm, and it's going to be small compared to this delta here. But furthermore, because we're taking this U to be contractible, we can use Poincaré's lemma and a little argument to show that, in fact, all these classes in this small ball can be represented by closed one form with small C1 norm and that vanish on U. So now we look at alpha plus beta, right? Alpha was our original closed one form, and beta are these representatives that vanish on U and represent each class in the neighborhood of 0. So what happens here? On U, basically nothing is changing because it just vanishes. So you remain with the 0 that you already have. And away from U, because we are small enough, you're not creating any new zeros. So alpha plus beta, the 0 set of alpha plus beta is going to be just the 0 set of alpha. And the C1 norm of alpha plus beta is going to be bounded above by the C1 norm of alpha, which is fixed, plus some delta over 2, which is just some constant, which only depends on alpha. And let's call this constant some CA. Okay. But now we just note that an epsilon neighborhood of A is just A plus the epsilon neighborhood on the origin. So every class here can just be written down as alpha plus beta in exactly this way. So what we've done, we showed that for a neighborhood of A, we can represent it by a closed one form whose C1 norm is less than CA and which has only 1, 0. Now, like I said, we can assume that that A had norm 1, so we just complete the argument by compactness. We can do it for a cover, extract a finite cover, and maximize over the A's. And now what we get is that everyone in this sphere, every class in this sphere can be represented by a closed one form with at most 1, 0, and with C1 norm bounded by C. And then you just scale, and you get the lemma. The map, we don't need it to be continuous, yeah. But so let me just recall what we showed, because I mean, if you got lost in the proof, I'm sorry for that. But so we showed that we have a map from non-trivial classes in H upper 1 to to closed one forms, right? That takes a class to a representative, such that the representative has at most 1, 0, and its C1 norm is controlled by the norm of A in a uniform way. A being the class. Okay. So now, well, this is just a theorem about closed one forms. Now let's look at it in a symplectic way. And what we can extract from this lemma is the following. Well, for any epsilon, we can find the neighborhood of the identity U epsilon here, such that every non-trivial cohomology class in this neighborhood, well, is represented by such a one form that I've been talking about for the past 20 minutes. But this one form, furthermore, will induce a symplectic isotopy via this equation here. And the time one map of this symplectic isotopy will have at most 1 fixed point, because we're controlling the C1 norm. So this is just, there's a bijection between fixed points and zeros of alpha. And furthermore, we can control the C0 distance of the time one map to the identity, basically because this is controlled again by the C1 norm in particular. And this last property is always good because in the end you want to compose maps and cancel out fluxes, so it's always good to know that if the class A is there, that it's symmetric. And if you have any open neighborhood that satisfies 1 and 2 of the origin, but not 3, let's say you have U doing that, then you just take U intersect minus U, and then you get the third property. So that's no trouble. Okay. So now, before going to the main proposition, let's have like a toy model for it. Let's try to do the C1 case, see how we can relate the two things. So let's show that with this corollary, right, that I just stated, one can show that the strong Arnaud conjecture for C1 small Hamiltonian diffeomorphisms, and when I say C1 small, I just mean the endpoint, not the whole path. If the whole path is C1 small, then this is the fact that the Arnaud conjecture holds is much easier to show. But let's show that the strong Arnaud conjecture for C1 small Hamiltonian diffeomorphism is in fact equivalent to the discreteness of the flux group. Of course, this is known. Both statements are known. So the first statement is known by theorem C, and the second statement is known by Ono. But what I want to show is that the corollary provides a way to connect them directly, basically. So let's first look at this implication. And this is what we're going to do, right? This is just a model for what we're going to do next. We want to show that if gamma has an accumulation point, then we can produce a Hamiltonian diffeomorphism, which is C1 small and has few fixed points, or less than one, basically. Yes? Yeah. Oh, yes, that's a great question. Yes, so the induced isotopy, the flux of the induced isotopy is going to be A. Yeah, sorry. Thank you for the question, because that's crucial. Okay. So let's prove this implication. Now, because gamma has an accumulation point, we can pick a loop of symplectic diffeomorphisms with an arbitrarily small flux. So in particular, we take a loop of symplectic diffeomorphisms whose flux lies in that U epsilon that we constructed and in the flux group, and is non-trivial. Now we take the induced isotopy by that corollary, which has few zeros and which is small, and compose it with this loop. And, well, let this composition be xi-t. Then, by construction, the time-one map of xi-t will be Hamiltonian, right? Because the flux of xi-t is A. By construction, the flux of this guy is minus A. It's a homomorphism, so they cancel out. And the number of fixed points of xi, because this is a loop, is just going to be the number of fixed points of this guy. And by everything I've been telling you, that's going to be less than or equal to 1. And because we can take this arbitrarily small, because it's an accumulation point, we can also make sure that psi is C1 small. Now, conversely, if Ham is C1 small, then its graph is going to lie in a Weinstein neighborhood of M cross M, and it's going to correspond to a graph of a closed one form, which a priori we don't know if that graph is exact. Oh, sorry, if that one form is exact. Now, like I said before, you can use this deformation of the graph of the one form to the zero section to induce a path of symplectic diffeomorphisms that's going to connect phi to the identity with a small path. And this will give you a symplectic loop, right? Because you were C1 small, so you could strafe pretty far away. The endpoint was C1 small, and now you've just completed the identity. But the long part of the path was Hamiltonian, so that has no flux. So all the flux that you have comes from this one form, and it's actually equivalent to the class of this one form. But because gamma is discrete, this cannot be small, arbitrarily small. So if you just take phi to be C1 small enough, which is going to control the norm of this class, we in fact know that the class is going to be trivial. So theta is going to be exact. And once we know that theta is exact, then the fixed points of phi is going to they're going to correspond to critical points of a smooth function. And if it's non-degenerate, the function is going to be Morse. So you get the stronger conjecture. Okay. So now that we are done with the easier case, let's deal with the C0 case. So I just recall the proposition here, and I'll recall again what we're going to do. We're going to show that if gamma 0 has an accumulation point, then we can produce a Hamiltonian diffeomorphism, which is C0 small and has at most 1, 0. Okay, so how does this go? Well, it's enough to show that gamma 0 is discrete, right? It's enough to show that it's discrete and that the origin has no accumulation point. So this is equivalent to showing that this intersection is trivial for a sufficiently small epsilon. So we take an arbitrarily small epsilon and take a non-trivial class A in this intersection. So this class is in gamma 0 and in the neighborhood that we constructed. Because why? Well, we want to represent this class by that special one form that with few zeros. So the flux of that, so I'm just calling alpha that one form. So the flux, what Pierre Alexandre asked, the flux of the induced path corresponding to minus alpha here, this is just going to be minus A. It's going to have, the time one map is going to have at most one fixed point, and it's going to be C0 close to the identity. And we would like to do the same thing as we did before, right? If we had a loop, we would just compose with a loop with the same flux and argue in the same way. But we don't have a loop, but we have like an almost loop, right? We can take this endpoint to be arbitrarily close to the identity in the C0 sense. So what do we do? I'll first say in words, and then I'll try to illustrate. So let's first consider the case that we have no fixed points, that that one form is non-singular. Then take delta to be the minimum distance between x and its image under the time one map. And of course, this is less than epsilon, right? Epsilon being the epsilon of u epsilon, because this is bounded above by the C0 distance of psi minus epsilon and the identity. Now, since A is also in gamma 0, now we're going to use this almost loop interpretation. We can find a path, a symplectic path, whose endpoint is arbitrarily close, C0 close to the identity, whose flux is A. And we're going to compose in the same way as before. Perhaps in a different order, because now it matters. Before it was just a loop, so it didn't matter. And we take this, the endpoint of this path to be C0 small, well, less than delta over 2 here, but C0 small in terms of the distance that the initial map is from having a fixed point. So now you look at this composition, and well, this is again going to be, the endpoint is going to be Hamiltonian because the fluxes are going to cancel out. And furthermore, it's only going to have, it's not going to have any new fixed points. And so now let me try to show you with a drawing. And here it's, I'm drawing the diagonal in M cross M. You could also think of this as the zero section in the cotangent bundle. And if you prefer this, just slightly tilt your head, and that will do the So what we have is we start off with the graph of phi minus psi minus alpha, right, which is that symplectic path that we chose with no 0 and with no fixed points. So that's going to lie at some distance from the diagonal. Now, what I'm saying is we can pick the endpoint of that almost loop that represents the same flux arbitrarily small. So its graph is going to lie arbitrarily close to the diagonal. And in fact, you can make it lie so close that when you compose, you're not going to create any new fixed points. Right? In particular, the distance between phi x and minus x is bounded below by this difference here. And this is positive. So you created a Hamiltonian diffeomorphism with no zeros and with C0 small distance to the identity, because these two maps are C0 close to the identity already. Okay? Okay, so now we're left to deal with the case where there is one fixed point. And the idea is going to be very similar, but it's much harder to execute. And it's basically a combination of the first case and the lemma for the one forms. Like the moral of the story is going to be very similar. So what we have here is exactly the same case, but now that representative, it could have a 0, right? We're just dealing with the case where it had none. So now let's suppose that it has 1, 0, so its graph in M cross M is going to look something like that. Now, if you just take a small, if you just try to do the same thing as we did before, and take almost loop whose endpoint is arbitrarily close to identity, when you compose, you technically could create plenty of new fixed points in this neighborhood. But there's this fantastic trick of Buchowski, Humilier, and Seyfadini that allows us to, by passing to M cross M, you can suppose that this endpoint of this almost loop is supported away from a small ball. And we can take this small ball to be precisely at the fixed point that we have. So now, of course, this is much easier said than done. There are a lot of analytical parts that you have to check that things still converge in the right way. But morally speaking, that's what we do. And once you know that this endpoint is supported away from the ball, now you can compose. And compose in a way that you're not doing anything in a neighborhood of the fixed point. So in the neighborhood, you're not changing the fixed point, so you remain with the fixed points you already have. But you can take this path again to be arbitrarily close to the diagonal in the C0 sense. So you can do it in such a way, and in a very similar way as before, that you're not creating any new fixed points away from this neighborhood. So in the end, when you compose exactly as you did before, you get a Hamiltonian diffeomorphism with only one fixed point, and which again is C0 close to the identity for the same reasons as before. So what did we do? Well, we showed that if gamma 0 has an accumulation point, then you can produce a Hamiltonian diffeomorphism with at most, a C0 small Hamiltonian diffeomorphism with at most one fixed point, which precisely proves this proposition. Any questions at this point? No. Okay. Now, I promise some new cases of the C0 flux conjecture. So here it goes. And this is a different story. It does not follow from the discreteness of gamma 0, but in any case, we can also, as part of the same work, we can achieve these new cases. So under the assumption that your symplectic manifold is spherically monotone, and by spherically monotone here I mean that the symplectic, the cohomology class of the symplectic form is proportional to the first Chern class on spheres, and this proportionality constant can be, it's non-negative. Then the C0 flux conjecture holds in either of these three cases. So if Euler characteristic is 0 or fundamental group has finite center, then the flux conjecture holds. It's not written here, but because this is a recent development, in this situation here, we can also show that the flux conjecture holds if your symplectic manifold is of Lefschetz type, for example. So any Kähler manifold with non-zero Euler characteristic or whose fundamental group has finite center. Furthermore, if this proportionality holds over all of H2, not just spherical classes, so usually what people call monotone, then the C0 flux conjecture just holds with no further assumption. So ham is equal to ham 0. And finally, we have this more technical condition here that basically says that if you can, by comparing dimensions, pick out paths whose endpoint paths such that the flux is in gamma top but not in gamma. If for any path whose flux is in gamma top but not in gamma, the dimension of the fixed point for homology is different than the total Betti number. If that's always true, then the C0 flux conjecture holds. And the reason why we have this condition here is that this allows us to find some examples of spherically monotone mapping tori where the C0 flux conjecture holds, but gamma top is not equal to gamma. So it wouldn't even fall in what was previously known. So they're provably new examples because it's usually hard to show that gamma top is not equal to gamma. And furthermore, we can show that the map from Sim0 to H up, so the flux map from Sim0 to this quotient is C0 continuous. And this is new, I think, even for general tori. And I mean, the first time I approached this question, I thought, okay, well, let's look at this map. Let's show that it's C0 continuous, and then you get the C0 flux conjecture. And the reality is quite the opposite. It's much, somehow it's harder to show that this map is C0 continuous than showing the flux conjecture. True, but anyways, now for these situations, we know that the flux map is C0 continuous. And well, that's what I prepared for today. Thank you very much for listening. And as I promised, here is the list of some notable contributions to the Arnaud conjecture. That's it. Thank you.